Okay, page 3, probability distributions. Example number 3, passive-aggressive traits. An industrial psychologist administered a personality test for passive-aggressive traits to 150 employees. The individuals were given a score from 1 to 5. 1 was extremely passive, 5 was extremely aggressive. A score of 3 indicated neither trait. So here's our results. We had 24 employees with a score of 1. So remember that was 100 150 employees. And remember, this is a capital N because this is all the employees that were tested. So out of all of them, 24 were score of 1, which comes out to 0.16, 33, 0.22, 42, 0.28, 30. Remember, if you're leaving them in fraction form, they need to be in reduced fraction form. I just find it easier to make them a decimal. That way I don't have to bother reducing them. It depends what the homework calls for, if that's what you're putting this into. And remember, we want to double check that these decimals add up to 1, right? Because all our probabilities should sum to 1. Notice all of our probabilities aren't negative numbers, and that looks good. So we need to interpret our data here. Would the data suggest that the sample of employees were mostly passive? Passive, aggressive, or neutral? Well, right here is 0.28 for a score of 3, which is our largest probability here. So I'm thinking neutral. Let's see if I can make this smaller so we can see them all at the same time. If one of these employees were picked for an assignment, is it more likely that he or she would be extremely passive or extremely aggressive? Let's see, extremely passive was a score of 1, which was 0.16, and extremely aggressive was 5, a score of 5, and that was 0.14, so it's more likely that they would have a score of 1. Probability that employees being rated a 3, let's see, 3 back up there was 28%. Between 2 and a 4, you can just add the probabilities up. That's a 2. Let's see, a 4 was a 0.2, so that's going to be 0.7, or 70% chance it's between, the employee was between 2 and 4. 1 or 5 is 0.16 plus 0.14, or 1 minus 0.7, which is 0.3. Not being extremely aggressive is values that are less than or equal to 4, so you can just do 1 minus 5. 1 minus 5, and 5 is a 0.14, which is 0.86, or 86% of the employees were not extremely aggressive. If a superior thought that this would be unusual for an employee to be in the sample to be rated with a 5, would he be correct? Note that unusual is typical, less than or equal to 0.05. Well, he would not be correct because ours was 5 or 0.14. So no, there's a 14% probability. So it's not unusual. Okay. So of particular interest, we want to talk about the mean of these values to get an average rating on our employees. We could have done that. For this one, it says what we need to do to to find is this formula, sum of the x's times their probabilities. And we want to make sure we're understanding the population designation here. Population mean or expected value. The expected value of a discrete value can be found by summing up all the products and probabilities. So population mean is also considered an expected value using the formula. And then you can also find a standard deviation and a variance as well. And there is 2 different ways to do that. It's up to you. Pick away. As long as we get the same answer, I'm good. You can see here that you have, back to the example about Nancy having expected value number of days. So what's her average? If we can expect her to show up both days of the week 80% of the time, what is her average when we take everything into account here as far as how much she shows up to class for 2 days a week? So we take our x's, which is 0, 1, and 2. We figure these probabilities were given to us, how much she shows up on a typical basis. You take your random variable number times your probability that's given and get a number. You add them all up and you get your mu, or your expected value. So if she's a class 2 days a week, given the information we have about her, her average that she shows up for classes 2 days a week is 1.78 days. Okay? And then we use this to put in to find our standard deviation. So we take your x, subtract it from the mu and get your deviation, and then square that deviation times the probability, which is 0.02 in this case, and get this number. Keep lots of your decimals. Do it again and again and again, and then you add them, and you're going to get the 0.116. That value is your variance, so you want to square root it to get your standard deviation. And the other one is just another way to plot this out and use the mean at the end. Okay, get all your sums first, then subtract the square of your mean. This comes out to, this total comes out to 3.38, and then we're going to subtract the square of the mean from that. 3.38 minus 3.1684. Remember, orders of operations, you have to square first and then subtract, and you'll get the same number that you need to square root and get your standard deviation. Okay, so how much she varies from 1.78 days is about a half a day. Okay, just to remind you that expected value of a discrete random variable is the mean. Okay, sometimes it's referred to like that. The standard deviation of a discrete random variable is the measure of risk, how much it varies. Okay, so let's try another one all by ourselves. Hospital, a researcher is interested in the number of times the average post-op patient rings for the nurse during a 12-hour shift. A random sample of 50 patients were taken. Okay, find the expected value. So we're going to ask all 50. Okay, so we're looking for a mu, which is our expected value, our mean, our population mean. Okay, so X is the number of times they ring. So apparently they ring, like, look right here. 4 patients did not ring for a nurse in a 12-hour shift. Okay. Apparently the most that they rang was 5 times, and 2 patients did that. Okay. Which gives us our 50 patients. When you add up your frequencies, make sure we talk to everybody. That's a population, capital N for that, for the number, sample number. And then you take each of the frequencies and divide it and get your relative frequency. So let me do this pretty fast. This is going to come out to 0.32, 0.28, by 50 is 0.12, 0.04, whoops, sorry, that's what happens when I go fast. Eight divided by 50 equals 0.16, 0.32, 0.28, 0.12, 0.04, right? 2 divided by 50. That, when you add up this column, is apparently a 1. And then you take your x and you multiply it by that. So this is going to give you a 0. 1 times 0.16 and so on. So this is 0.16, 0.64, 0.84, 0.48, and 0.2. And I added these up, and they do come out to a 2.32 for my expected value. Now, does that seem reasonable? Look back over here. What's going on? Most patients rang for their nurse about 2 or 3 times. So it seems reasonable that we get an expected value of 2.32, because it seems like that was the most common amount of time, so that you can plan your staff to meet those needs. Okay, here's another one. It can take anywhere from 3 to 5 years to earn a Bachelor of Science degree, a BS. Here's the distribution below. How many years can someone expect it to take to earn their degree? So these are the given probabilities that we have. 1 is missing. So remember, this is supposed to add up to 1. So you take the 0.05, 0.4, 0.3, and 0.1 and add them up, and you get 0.85. So 1 minus 0.85 gives you 0.15. That goes here. Okay, so it will sum up to 1. Then we make sure that we're multiplying these numbers, these random variables. Apparently, that's what they figured it would take. So we're going to use all of them times the probability that we found. This is going to be 0.15, 0.4 is 1.6, 1.5, 0.9, 0.7. Remember, these aren't probabilities. This is your random variable times the probability, and it's going to add up to your mean. So if you look at it, this seems to be where the larger probabilities are. So it seems reasonable that we get a 4.85 for our expected value. You can expect to take over 4 years, almost 5 years, to get your degree these days. Okay? All right, last one. Nope. Done.